In this video, I'm going to discuss the double integral. The notation for the double integral of a function of two variables is this. What is R? Now, recall the definite integral in the situation of function of one variable. We normally write it like this: integration from a to b of f with respect to x. The same can be written as integration over the interval a comma b, closed interval, of the function f. That is the kind of convention I'm using over here. So R is a region of the xy plane. So I'm considering R to be this region of the xy plane. So it is the collection of all points within this curve. So what is the meaning given to this particular notation? What is the value for this particular notation? So let me call that value as I. And what these two lines basically codify is how is this value to be obtained? How is the value I to be obtained? So look at the bracket. What is this bracket saying? It is saying that integrate f with respect to x, but treat y to be a constant in R. So I have fixed a value of y, and if you move along this line, the value of y is not changing. But then there is a dy which says that you are actually supposed to look at a very thin strip along the y-axis. But we are going by the understanding that this thickness is so small that y is hardly changing. Okay? And therefore, what is changing is x, and as you move along this line from the left to the right, the smallest value of x that you come across will be the x lower, x sub L, and as you reach the other side, you will come across the maximum value of x along this particular line. I'm denoting that by xu. That is going to determine the lower limit and the upper limit of this integral. And if you're considering this small thickness, what you have actually done is carried out integration over a very thin strip parallel to the x-axis. And what is the meaning of this particular symbol? You're supposed to integrate over all values of R. So what we have accomplished is integration over a thin strip. Integration over other points remain. So what you can do is you can fill this region R with thin strips of this kind, and the lowest level of this strip will correspond to the lowest point in this particular region R, and the highest level of the strip will correspond to the highest level of highest value of y in this particular region R. So this is what this symbol actually means. The actual evaluation will be shown with the help of an illustration, with the help of an example. Now, instead of carrying out integration first with respect to x and then with respect to y, you could have done it in the exact opposite way. And this particular line is just that. So if you decide to carry out integration first with respect to y, you need to consider x to be a constant, again in the region R. So if I have to evaluate this particular line, if I have to carry out the evaluation as per this line, then what I do is I fix a value of x. And if you go along this particular line parallel to the y-axis, what is changing is y. The value of x is fixed. The lowest level, or rather the point where the line starts, that will determine the lower limit of y. I'm calling it as YL. And as you hit the topmost point, when you hit this particular curve, you get the highest value of y, which I'm calling as YU. Now the values of YL and YU will depend upon where you have fixed x. So if you fix x, for example, somewhere here, then you have a different value of YL and a different value of YU, and so on. Okay. Alright, so if that is what you have done, then you have carried out integration over a thin strip. But then you are supposed to integrate over the entire collection of points in R. And so what you can do is, you can choose strips of this kind to fill this region R. Alright, and the leftmost position of the strip will determine the lower limit for x, and the rightmost position will determine the upper limit for x. Okay, we'll see all this through an example. So let me take an example now. I will take this example. I'm taking a very simple example. So the region R is the collection of all these points, all right? And the equation of this particular line is given by x plus y equal to 1. You already know the equations of the other lines, for example, this and this. This is your x-axis, this is your y-axis, and this is your origin as usual. Now I wish to evaluate this. Let me give it a name. Let me call it as so I call the value of the integral as I, and I wish to integrate first with respect to x. So this is same as integral of xy dx dy, and for this part of the integral, y is a constant. All right. So I fix y, and as I move along this line, x changes, and x changes from 0 to the value of x determined by this particular equation. The value of x over here is 1 minus 1. That is going to determine the lower and the upper limits for x. And then okay, so now if you are considering this, you're actually looking at a thin strip along this particular line. All right, and integration over R would mean filling up the strip by such strips. The lowest position of this strip would be when the strip coincides with the line x equal to 0, y equal to 0, and the highest will correspond to this particular point here. Now you can work out the coordinates of this particular point looking at this equation. X is 0, y is equal to 1, and for this I don't need it as of now. Okay, so y equal to 0 to y equal to 1. Now when you're working the bracket out, your y is a constant. It has been mentioned above. And if y is a constant, you are familiar with how to do this. That's very easy now. So y is a constant. You integrate x, what you get is x squared by 2. and then you can use the upper and lower limits. This is 1 by 2 integration 0 to 1. All right. The lower limit is going to give you 0, so there's nothing from there, and the upper limit will give you y times 1 minus y raised to 2 dy. Now that's something which you have done in school days, integrating function of one variable. So you can work this out. Just check. I think this value will turn out to be 1 by 24 if I've done it right. All right. So in this particular calculation, I have done the integration with respect to x first, and then with respect to y. So first with respect to x and then with respect to y. All right. Let me just do it the other way, namely first integrate with respect to y and then with respect to x. And let us just see what is the value going to be. So I start from here and I write it like this. After doing this, I will integrate with respect to x. But when you are doing this part, when you are integrating with respect to y, x is to be treated as a constant. All right. Okay, and if you do that, y is going to change from some place to some place. Okay, x is to be kept constant. So what I do is, in this particular region, you fix an x. So suppose I fix x over here, x is fixed, and in this region x is going to be a constant along this line. Okay, and if you are considering what is there outside, so you are looking at a small thickness, a strip parallel to the y-axis. The lowest value of I, the smallest value, the lower limit of x is, the lower limit for y is going to correspond to this particular value of y, which is 0. And as you go up, you will hit across, so you can find the value of y from this particular equation. So y equal to 1 minus x. And now you can consider filling this entire region by strips, vertical strips. All right. And the leftmost position of the vertical strip would be at x equal to 0. All right. And the rightmost position will correspond to this particular point, x equal to 1. Okay. Now this is very easy, because for this part, x is a constant. Okay. So what you have is integral of x 0 to 1. Let's evaluate this. X is being treated as a constant. You are integrating with respect to y. So what you get is x y square upon 2. Substitute the value of the limits, y 0 to y equal to 1 minus x, and then you integrate with respect to x. This is equal to 1 by 2. Lower limit is going to give you nothing. Upper limit will give you okay. So if you just do this, you will get the same answer, 1 by 24. Okay. So in this particular case, the order of integration doesn't seem to be important. Is that the case always? The answer is no. But for nice functions, Fubini's theorem tells you that the order of integration is not important. Whichever order you choose, the value will always turn out to be the same. Alright, so I hope you have understood this particular example. I will just make a few remarks. So the first one is that the order of integration is not important, provided your function is nice enough. Okay, In engineering applications, we'll always come across nicer functions where we really don't have to worry much about the order of integration, especially at the first year level, even in the second year level. So we are not going to come across complicated situations where the order of integration gives you different values. All right. Okay, I think that's all for the introduction. If you have understood this particular example, you should not have difficulty in working out problems on the double integral. In the subsequent videos, we will try to understand how to choose the order of integration intelligently. Sometimes if you choose the order of integration nicely, the task of or the tediousness of the calculation can be reduced to a large extent. Okay, so we'll see that in the next video, and in the subsequent videos we will also see how to work out the double integral when the function is not given in the Cartesian system but it is given in the polar system. That's all for now.